All right, so what I want to talk about now is I want to talk about this idea of the inverse, and in fact, how linear combinations play into the inverse. The idea of the inverse is really, really necessary because it turns out that we're going to need it in order to actually solve equations. So let's say, for example, I've got an equation, and my equation is 3x is equivalent to 7 mod 8. Okay, so 3x is equivalent to 7 mod 8. Now, normally, if we're going to do algebra, right, if you had 3x equals 7, okay, then what you do is you'd multiply, you take 1/3 times 3x, and that equals 1/3 times 7, okay, and so that means that x equals 7/3. Well, in number theory 1, we don't actually have a division, or not this kind of division. We talk about divisibility, certainly, but we don't have an algebraic kind of division. Not only that, 1/3, okay, is not a member of modulo 8, okay? It's not an integer. And so consequently, we don't get to multiply by 1/3. We've got to do something else, okay? But what we're going to do is we're going to utilize the idea of the inverse, okay? So the whole reason why we multiplied by 1/3, okay? The whole reason why we multiplied by 1/3 is because 1/3 times 3 equals 1. So 1/3 times 3x will end up equaling 1x, which is just x. So what it does is it isolates for us, right? From an algebraic perspective, that's what it's doing. So what we need, okay, so what we need is a number mod 8, okay, that when multiplied by 3 gives us 1, if such a number even exists, okay? So we want to know a number that when I multiply it by 3, it will end up giving me 1, all right? And so let's take a look at what those numbers might be. So first, let's kind of review a little bit about what we mean by counting in modulo, all right? Because that's going to become really important, all right? First, when we say something like, for example, uh, 15 mod 8, okay, this is going to equal r in the equation, okay, our remainder in the equation 15 equals 8 times 1, in this case plus 7, right? So it's our remainder here inside of the division algorithm, in the equation for the division algorithm. And so that's what 15 mod 8 is, okay? It's basically that remainder. So 15 equals 8 times 1 plus 7. So 15 mod 8, okay, equals 7. Now, 15 is not the only number that actually has 7, right, as its modulo 8. 22, for example. 23, sorry, 23 mod 8, okay, will also equal 7 because 23 equals 8 times 2 plus 7. So its remainder again is 7. All right? In fact, anytime we take any one of these numbers and we add or subtract 8, okay, so we add or subtract 8 away from them, we're going to end up with something that is mod 8 is going to equal 7, right? And so it's equivalent to 7. So we say that 23 is equivalent to 7 mod 8, okay? And 15 is equivalent to 7 mod 8. If you want to know more about this, you could actually go in and watch my video on modulo, okay, and how to do modular arithmetic. So we have that. We have 15 is equivalent to 7 mod 8. We have 23 is equivalent to 7 mod 8. There's lots of things that are equivalent to 7 mod 8. And here's kind of why it happens that way, all right? It's kind of a counting. So we'll start, let's say, for example, we'll start at 0. Okay, we got 0 and 0 mod 8. Okay, so this is in in the integers in z, okay? And then this one here is going to be in z8, all right? What are the values? And z8 is just where all we're doing is we're counting by eights, Okay, so 0 is 0 in Z8. 1 is 1. 2 is 2. 3 is 3. 4 is 4. Okay, 5 is 5. 6 is 6. 7 is 7. 8 is now actually 0. All right, so what we've done is we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 integers, right, representing all the values in modulo 8. And then once we get up to the next multiple of 8, we're going back to 0. Okay, so 9 is actually going to be 1. 10 will be 2. 11 will be 3, and so on and so on and so forth. Okay, so here's the thing, right? If you notice anything, right, that is basically that has the remainder of 7, right, it's going to have a 7. Yes, if I continue to move up on these integers, 12, that's going to be 4. 13, that's going to be 5. 14 is 6. And then 15, we could see is going to be 7, right? Or we go backwards, okay? Negative 1 is actually going to be 7, 2, okay? So basically, if I start at 7 and I subtract 8, I'm going to get back to another value that is going to be equivalent to 7. All right? So they're all going to end up being equivalent to 7. Now, we're interested in the ones that are equivalent to 1. Okay? So you can see right here, 9 is equivalent to 1. 1 is equivalent to 1. If I add another 8 to 9, I'm going to get 17. So 17 is also going to be equivalent to 1. And if you think about it, 17 is 16 plus 1. So that's 2 times 8 plus 1, right? Every multiple of 8 is going to be a 0, okay? So every multiple of 8 plus 1 is going to end up being a 1, right? And so we're really going to be looking for those ones. We're looking for those ones, and we're going to figure out what it is that I can multiply my number by to get to one of those ones in modulo, in this case, modulo 8, or in modulo m, whichever modulo m I'm looking for. So let's take a look. We wanted to say 3x, right? We wanted to see what that's equivalent to 7 mod 8. Okay, 7 mod 8. And so what I need to do is I need to figure out what number times 3 is, times 3 is equivalent to 1 in 1 mod 8. All right, so one of those 1 mod 8s. So I'm going to try it out. I'm going to see which ones it is. So I'm going to start with 3 times 1. So 3 times 1 is 3. All right, we'll talk about that in a second. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. 3 times 5 is 15. 3 times 6 is 18. And 3 times 7 is 21. Now, 3 is equivalent to 3 mod 8. So that's not it. It's not 1. Okay? 6 is equivalent to just 6 mod 8. But 9, okay, 9 is going to end up being equivalent to 1 mod 8. All right? Because 9 equals 8 times 1 plus 1. There it is. Its remainder is 1 when we divide it by 8 using the division algorithm. So the inverse of 3 is 3 in modulo 8. Now I can solve my problem. I had 3x is equivalent to 7 mod 8. I know that if I multiply both sides by 3, on the left-hand side, I'm going to get 1. So this is going to be 3 times 3x will be equivalent to 3 times 7 mod 8. Okay? Because we're going to multiply both sides by the same number. That's algebra. 3 times 3 modulo 8, remember, is now 1. So this is x is equivalent to 21 mod 8. And now all I got to figure out is what exactly is 21 in modulo 8. So 21 equals, okay, 21 equals 8 times 2 plus 5. So x equals 5. There it is. That's my remainder. So now x is going to end up equaling 5. We go and we check. 3 times 5 equals 15. And that actually is equivalent to 7 mod 8 because 15 equals 8 times 1 plus 7, right? And that's that value. And so we've solved our equation. When we do congruences, this is what we're going to do, all right? Okay, so now what I'm going to do is I'm going to go and I'm going to show you how we're going to use linear combinations in order to, in fact, find an inverse. So I have a theorem. And the theorem states this: if two values are relatively prime, then, okay, then each has an inverse modulo the other value. That's not the greatest math statement, but I'll show you what I mean. Modulo the other value, okay? So for example, all right, we had 3 and 8, okay? 3 and 8, we saw that 3 actually had an inverse modulo 8. And it turns out that 8 is going to have a modulo inverse 3, 8 will have an inverse modulo 3 as well, okay? 3, the GCD of 3 and 8 is equal to 1, all right? So 3 has an inverse modulo 8, and 8 has an inverse modulo 3, because basically the idea here is that if two numbers are relatively prime, then, okay, then basically what we're never... The reason why this is true has to do with linear combinations, okay? So just for right now, you can go and figure this out on your own. But the linear combination for 3 and 8 that gives us 1, right, is because we get 3 times 3 equals, or 3 times 3 minus 8 times 1 equals 1, okay? And by an earlier proof, we actually established that the GCD can always be written as a linear combination using the algorithm that we showed, okay? So if two numbers are relatively prime, that means that their GCD ends up equaling 1. Their greatest common divisor is 1, and so consequently we can write those two numbers, okay, as a linear combination equaling to 1. And this is where this idea comes in as to how we're going to find the inverse. So in modulo 3, 3 times 3 equals 0, okay, mod 3, because it's a multiple of 3. Any multiple of 3 is going to end up equaling 0 modulo 3, right? And that's kind of that idea that we were talking about when we talked about 8, right? In modulo 8, every time we get to another multiple of 8, we're going to go back to 0. In modulo 3, every time we get a multiple of 3, we're going to go back to 0. So that means negative 8 times 1 has to equal 1. All right, basically what we get here is we get 0 minus 8 times 1 is equivalent to 1 mod 3, right? And so negative 8 times 1 is going to be equivalent to 1 mod 3. Hence, negative 1 is the inverse of 8 in modulo 3. Okay, the scalar, right, which is end up being negative 1, right, the negative 1, okay, is the inverse of 8 in modulo 3. Conversely, if I have 3 times 3 minus 8 times 1, okay? And that equals, or is equivalent to 1 mod 8. Now what I have is negative 8 times 1, this equals 0. So I have 3 times 3, right, plus 0 is equivalent to 1 mod 8. And so consequently 3 times 3 is now equivalent to 1 mod 8. And that means that 3 is the inverse of 3 in modulo 8. And so basically that's how we're going to use our linear combinations in order to determine the inverses for particular numbers. Okay, so let's take a look at a couple of examples. So the first one is one that I did in an earlier video. We had 36 times 2 minus, 71 times 1 equals 1. And actually, I'm going to rewrite this so that I have my scalars in front. So this could be 2 times 36 minus 1 times 71 equals 1. All right, so the inverse of 71 in modulo 36 is negative 1. And just to give you a sense, negative 1 is 70. Oh, excuse me. Negative 1 is 35 in modulo 36. So basically what it is negative 1 plus 36. So we'd say, okay, so 35 is the inverse of 71. Okay? And then the inverse of 36 in modulo 71 is 2. All right, so there that is. Its scalar is 2, right? 2 times 36 is 72. That's 1 more than 71, so it's clearly 1 modulo 76. Okay, and you could actually check that 35 times 71 divided by 36 gives you a remainder of 1. Okay, so there's the first one. Now here's the second one. What this is saying is that 29 is the inverse of 35 in modulo 78. Okay, and negative 13, okay, which is 35 minus 13, which equals 22, okay, is, so 22 or negative 13, whichever one you want to choose, is the inverse of 78 in modulo 35. And there it is. Both of them have inverses, okay? So now a note about prime numbers. Every number is relatively prime to a prime number, right? The only divisors for prime numbers are 1, so the greatest common divisor between any number and a prime number is always going to be 1. So they're always going to be relatively prime. So if m is prime, every number modulo m has an inverse. So those prime moduli, they're really, really handy, very, very special, because for every value other than the number itself, right, we're going to be able to find an inverse. All right, so that kind of completes the idea of how do we find inverses using linear combinations. So that's what one of the things we discussed, and also what basically was an inverse and why we use them. Okay, in our next section, what we're going to do is I'm going to do some linear congruences now that we've gotten to this point.